Hello, this is my lab 3 over circuits for physics 2. The purpose of this lab was to predict the behavior of circuits containing resistors in series and parallel. We use multimeters to measure the actual values of current and potential differences in the circuit, and we investigated the behavior of resistors and capacitors. Our findings was that the predicted and actual currents and potential voltages were similar. The measured resistance of the resistors for the first circuit was 45 and 105 ohms, which was different from the anticipated resistance. And when the resistance is increased, the time to charge and discharge the circuit increases. Key concepts for this lab was the loop rule, which basically says the change in the net voltage is zero. The total voltage change across a closed loop is zero. And the node rule, which says that the current in the node and out of the node are equivalent, or the sum of the currents is equivalent. We also had Ohm's law, change in the voltage equals the current times the resistance, and then this was rearranged, which was used later in the lab. And resistors in parallel, the total resistance is equivalent to the sum of all of the resistors resistance, but that is going to be under 1. So you have to divide. And then, but in series, you just add them up like normal. The model for this lab, our system was the ammeter or the voltmeter, depending on what the purpose was at the moment, and then the surroundings was the circuit. And in the bottom left, we have the second circuit that was observed, and the top right shows the first circuit. The first circuit, initially we found the current. So the predicted currents, we used the node rule, and knowing that a series circuit has the same current across resistors, because it was closed as well, we had a predicted current in the circuit was going to be 0.02 amps. And then when we measured it, it was pretty close to 0.02 amps in both areas, I1, I2, as seen in this image. Um, the ammeter, we then converted to a voltmeter, and the predicted current was still going to be 0.02 amps because they're still in series. And the actual was still 0.02. And in the bottom left, you can see a picture of what our series actually looked like. Potential differences. On the right, I have a diagram of all the different locations. So from A to B, that's just across the battery, it was 3 volts. B to C, it was 0. C to D, that's the 47 ohms resistor, and that was negative 0.9. Um, E to F across the 100 was negative 2.1, and then F to G, G to H to A, that was all 0. And then this is supported by the loop rule because when you add them up, it does equal 0. And then in the bottom left, I have a graph depicting. So from C to D, you can see a slope, and E to F, there's a slope, but otherwise it's just a constant because the change was 0. In the circuit one, we replaced the voltmeter with an ammeter in parallel with the 100 ohm resistor, and the current through the other ammeter increases to 0.6 amps because the current prefers the resistor with the lowest resistance. And then calculated resistance, we kind of worked backwards here. For the 47 ohm resistor, it's calculated to be about 45 ohms with our measured values. The 100 ohm resistor had 105 ohms instead, and the wire and the ammeter had 0 because they had 0 volts going through them. For our second circuit with the RC circuit, just some general observations for the circuit. When a battery is connected to the 10 ohm bulb and a capacitor in series and then it's charged, the light bulb will get bright immediately and then it will get less bright over time. And then when the battery is disconnected and the capacitor is directly connected to the bulb, and then it's discharged, the bulb will get dimmer over time. And then we measured the time it took to charge and discharge each bulb. For the 10 ohm bulb, it took 14.2 seconds to charge, and for the took 14.5 seconds to discharge. So very similar values. But then for the 20 ohm bulb, it took 22.3 seconds to charge and 21.9 seconds to discharge. So there is a difference in the values, but it's not crazy. But between the 10 and 20, we can see like almost double, not quite, but very close. So we can determine that the greater the resistance of the bulb, the longer it takes the charges to charge and discharge, and the longer it takes for the potential difference to decrease. In conclusion, the node and loop rules are fairly accurate for estimating the currents and potential differences of a circuit, and though close to the estimated values, the measured currents and potential voltages calculate resistances that were different than the intended values. And as resistance increases, the total time it takes to charge and discharge the resistor increases too. Potential sources of error, human error in timing the charging and discharging of the circuit, and inaccurate measures of current or voltages due to multimeter calibration. If we charged a capacitor with no resistor in the circuit, an infinite current would be created. and then it would reach full charge instantaneously and would take no time whatsoever. And this prediction could not happen in real life because the wires and capacitors have some resistance, though the amount may be very small. Perfect. Thank you.